Okay, so are there any questions from the previous lectures?
We're not just studying the properties of the Fourier transform, right?
Yes.
So we can find the Green's functions in discrete space.
Well, we are switching to the continuous case now, because in principle, in discrete case, everything is clear, because it is just some finite matrix that performs linear transformation on this space of functions. And in principle, you can compute the Green function for any difference operator. So, when we switch to the continuous case, we'll have questions about convergence, about proper definitions of some things. Originally it was just linear algebra, and now we will have some kind of analysis. So, let me remind the definition of the Fourier transform. So in the finite dimensional case, it was defined by this formula, that f tilde of k was 1 over square root of n, sum from 1 to n, then there is a definition for for the space of functions on the circle. So in this case, we have discrete Fourier modes defined by this: d phi over 2 pi plus infinity. Oh, sorry, from 0 to 2 pi. And there is a Fourier transform on the real line. So let us first focus on this case of S1, on the space of functions on a circle.
There's a normalization condition with the real line. Are you putting 2 pi in the other one?
Yes, it can be defined in different ways, but the most, well, at least for me, the most natural is to put 2 pi in the momentum integral, because in that case you always have a combination dp over 2 pi. Another option is to put 2 pi in the exponential, but people usually don't do this. Although it probably might be simpler in some cases. Okay, so first I want to study this case. So, what is the idea of this transformation? we can imagine that there is a space of functions. Uh, let me think. Mm, so So, the goal of our study, so there are several goals of our this study. Uh, so, we first want to study the behavior of the Fourier image of this function. And then to use this behavior to prove that the inverse transformation for this is given by simply taking the Fourier series with this coefficient. And third is to study the convergence of this series to our original function. Uh, so we can denote it by a fan, meaning that it is a partial sum given by sum from minus n to n.
What's that word?
Hmm?
The word with C convergence?
Yes. Yes. So, of course, to do all this, we need to know something about the behavior of these coefficients. So, at least we would like to be sure that this series for the inverse transformation makes sense. So let us proceed with this. Mm. So, as for uh, oh, as for one, there are so there can be at least two different statements about the behavior of these coefficients. So, like 1a, can call it this way, is about so is about convergence of their absolute values squared. Uh, so let us, so we need to impose some constraints on our function, because if you take an arbitrary function, then you can meet problems like non-existence of the C integral. And the first problem we can meet. So let us ask this function to be at least continuous. uh, actually, we can make it piecewise continuous, and it would also be fine. Well, maybe better to say that there are there is finite number of points of discontinuity. Mm, yes. So in this case, we can in this case the square product of f with f is well defined. So it's integral of f of phi star or f of phi, or maybe let us define square product of two different functions. So uh, and theorem lemma. I would like to prove that in this case, uh, sum of absolute values of this squares of the coefficients is bounded by a square of function f, and then this is less than infinity square. So I would like to prove that this is convergent, and uh, how to do this? We can prove the statement for any finite sum of the coefficients. So, and to do this, let us give some interpretation to this partial sum of fns. So, we can write that f. So first we can write that the Fourier coefficient in the series is given by a scalar product. Is a scalar product of I and phi with a function f. Or it can be it can also be called orthogonal projection.
So you're projecting onto like a basis vector that there's an infinite number of them.
Yes, yes. So if you write it this way, fn of phi is equal to a sum of e to I n phi, scalar product of I and phi with f. So it's the same as to say that it equals to a projector Pn acting on f of phi, where this orthogonal projector is defined precisely by this formula. So we can now check that this indeed projector, in a sense that Pn Pn squared equals to Pn. So it's true because if you substitute, if we if you try to compute its square, then what do you get? There's some um, like this. And when we can compute the first sum, the only surviving term will be for m equals to n. Because the scalar product of e to I n phi with e to I m phi equals to, like, what does it equal to? If you look at the definition. Yes. Yes. So the sum equals to, so from uh, to n phi m phi, so it's Pn f. Uh, there is also another projector. So there is Pn, and there is one minus Pn. So there is Pn, and there is identity minus projector. So it's a kind of projector on the complement. And this projector has the same property. So um, why do we need all this? Because I would like to write, to prove that something is greater than zero, I would like to write this expression as the absolute value squared uh, of some other expression. So, um, let's consider the scalar product. So, we know that it is greater than zero. Right, because it's a property of the scalar product. Mm. But so it's a trivial statement. But now let us substitute that HFN is our projector acting on F. So we can continue this equality as uh, 1 minus projector acting on F. 1 minus projector acting on F. Then open all these brackets. Oh, sorry. The scalar product of F minus 2 of scalar products of F with projector acting on F uh, plus projector acting on both functions. But all these expressions can be simplified to this form or to this form, which is all the same. Because first, projector squared is 1, and second, probably I should have told this, there is another property that we can move projector from the first to the second place in the scalar product. It's this statement means that it is a Hermitian, or yes, or self-adjoint. Maybe
General property of projectors.
of orthogonal projectors. So do we need to prove this? Well, let us actually prove the statement, because to prove it, we simply need to compute the scalar product and write that it equals to sum from n equals to minus n to n. Uh, uh, F scalar product I and phi times e to I and phi g. Alright, so you see that it is indeed symmetric, and the insertion of projector in a different place. Right. So we can move it freely between two terms in scalar product, uh, and so it's simply a sum of absolute sum of f bar times g, not all the whole set of integers, but only from minus n to n. Yeah, and as long we have this properties, we can transform this equation to scalar product of f with f minus a scalar product of Pn f Pn f. So it is a scalar product of f with f minus this scalar product can be written explicitly because projector electron f is given by a finite sum. So we can write that it is a sum from n equals to minus n to n absolute value of n tilde squared. So, are there any questions about this?
You use the orthogonal or the Hermitian property, so then you should get FF two FF, or don't we have two FF?
Why to
So that one and the last term.
uh, so these two and here we can write that Pn and Pn squared is the same, and then we can get two projectiles acting on each function. Hmm?
We wrote Fn times Fn under the product. Y is equal to 1 minus Pn. So I think it's maybe we just start from 1 minus Pnf, 1 minus Pnf, and that's greater or equal than 0, and then follow.
Probably. What is the question? So we start from this, right? This is greater or equal than 0.
And they are equal.
Hmm?
I don't see how the first equal.
It's just the oh, sorry, sorry. I should have written not this, but f minus fn. Sorry. Yes, it's not a reminder; it's a difference. Thank you for noticing this. Yes. So it is something that should go to 0 in the limit. So is it fine? So. So now we can consider this difference. We can transform all terms with projectors to the universal form, this one, and finally get desired equality. So you can, of course, do the same computation without inducing projectors. You can simply substitute the definition of a fan and compute everything. But for me, it seems that it's slightly more conceptual. So that you don't need to prove all the statements of projectors on the fly. Yes, we already know this restriction for fans. So in particular, we understand that all fans should go to zero. Otherwise, the series is not convergent. So we have at least this restriction. Now let us study the behavior if we impose more conditions on f. Mm. So uh, let our function f be differentiable. C1 is 1. Uh, in principle, let it first be differentiable. So in this case, we can get further restrictions on its coefficients. Then fn tilde is given by, as before, but this time we can use differentiability of the function f and integrate this by parts. So we can write that from 0 to pi. So this, and then integrated by parts. We have that it is integral from 0 to 2 pi, 1 over in. So we can say that it is uh, 1 over in some f prime tilde n. So here we knew that one corollary of this was that Fn was so at least Fn was going to 0. And also this, we know that Fn tilde prime, Fn tilde should go to 0. Well, then that series is convergent. So it is one restriction. Another restriction can be obtained by using the inequality that maybe there is an inequality of the product of two such functions. Well, let me write it. Fn tilde is 1 over n. Fn tilde prime is less or equal than 1/2 of sum of their squares. Let me write absolute value of this.
In the previous meeting, if a prime goes to 0,
Hmm.
I don't understand why if we put the prime.
Prime means simply that it is a Fourier coefficient of f prime. Because
It shouldn't be the f and t that goes to 0.
yeah, but it goes to 0. But this formula says that it goes to 0 with a specific rate. It goes to 0 faster than 1 over n. So, so is it fine? So we can say that Fn tilde is all small of 1 over n. So here we could write that Fn tilde was all small of 1. Right? So there is this restriction, and so we know that series of the former Fn tilde or integer ends is less than infinity. So this series is convergent in this case. So this will be important in the next steps. Right? So yes, and we see that there is such a requirement for one differentiable function, and but we can get the same differentiating it further. If it is differentiable many times, then we know that so if f is in scale of S1, then it's for coefficients behave as all of 1 over n to k.
I don't remember my analysis so much. Do we not have trouble having differentiable functions when we allow for pointwise continuity?
Mm. So could you say it again? Or?
Because at the beginning we didn't say that the functions had to be strictly continuous. We allowed pointwise discontinuities.
Oh, but we are studying different classes of functions. In a sense, this Fourier transform is defined for well for functions in L1. As long as we can compute that integral, then the Fourier transform is defined. And now we would like to study what happens with special classes of functions. So the message is that if you consider smooth enough function, then its Fourier coefficients behave nicely at big ends, and it also works for the Fourier transform on the real line. In that case, we will need to study its behavior at infinity, and the argument is precisely the same. So we will need to differentiate it as many times as we can and get such a restriction. So, so it is a kind of upper restriction, but let us see what happens if we have some function that is in general it's smooth, maybe infinitely smooth, but it has discontinuity in the k plus first derivative. So, mm, so so let us say that f is in uh, like it's another estimation. And uh, f k plus 1 is piecewise continuous. So a kind of k plus first derivative of this function almost exists. So let us see how its Fourier transform behaves. So we can differentiate it in k times. So we'll have 1 over I, 1 over in to the k, integral from 0 to 2 pi, k of phi. So now we can say that there are some files that correspond to the discontinuities in K plus first derivative. The sum over L, and here let us write sum of integrals from phi L to phi L plus 1. Sorry, I missed the exponential. And, when we have the integrals, we need to write yes, yeah. So if we have such integrals, we will have boundary terms. So
Are you breaking up the integral where the discontinuities are?
yes, yes. Let me write at phi else in the set of phi else. Oh, we can now integrate it by parts again, since discontinuities are the boundaries. So we have 1 over I n to k plus 1. There's some minus 1. And here we have sum over L of first of boundary terms. Minus this integral.
What is that L plus 1 subscript on the phi and the beginning of the sum there? The subscript L plus 1?
Yes, it's a number of this phi. Oh, so there are discontinuities at several points, right?
I'm just looking at the beginning of the expansion. What are the subscripts on the phi?
FL plus phi L plus 1, phi L.
Okay.
So, wait, I asked it to be a piecewise continuous. Let me ask it piecewise indifferentiable. Uh, with discontinuity that mm, no, I want f of k to be normal and f of k plus 1 to have some jumps.
But this should, if we can compute fk plus 1, then fk is differentiable.
Uh, uh,
This would mean that f is ck plus 1.
no, but fk plus 1 is not defined at some points. So it's not differentiable at all points. So, yeah. Is it fine?
Now it's usually on R, either if function is ck, then maybe we can compute the k plus 1 derivative
Mm, wait.
on R. Maybe on S1, since it's compact,
Oh,
right?
it maybe I'm missing the definitions. Mm, oh, so uh, so C0 functions are functions that are just continuous, right? Mm, C1 functions should be functions for which we can compute derivative, and this derivative is continuous, right? So, uh, mm, wait. Um, so if I write it like this, do I assume that it is continuous or not? So, okay. No, I meant different thing that that it is piecewise differentiable and continuous, in the sense that we can compute its derivative apart from points of discontinuity. Yes. Mm, continuous and differentiable. So I mean something like this, that we have a function that has discontinuity in its derivative, but apart from this, it does not have other problems. Like we don't have functions that are continuous and nowhere differentiable. So mm, I wanted to remove such pathological cases. Yeah. Uh, yeah, so if we have this, then we can compute this. We can integrate it by parts once again. That will be and so this sum alone cancels because fk is defined and it's defined every and each such term finds a complementary term from another integral, so this cancels. And if we compute if we integrate it by parts once again, then it would equal to uh, sum of minus I and phi l plus 1 f k plus 1 of phi l plus 1 minus and phi l f k of phi l minus this integral k plus 2 of phi. So now f k plus 1. So now these expressions do not cancel. So all this is all of 1. Therefore, nth coefficient, nth square coefficient of this function behaves like all of 1 over n to k plus 2. So the point is that if a function has some will behave discontinuities, then we have a control on its Fourier coefficients, and they behave slightly better than we could expect from the beginning. And let us see how it works in practice. Yeah. Also, a remark that once all these integrals exist, this works equivalently well also for the case of the real line, because this integral should simply go from minus infinity to plus infinity, and n should be replaced by p. So let's consider an example of this phenomenon. Probably I will erase this. And I propose to compute this Fourier transform in both directions. So suppose that we have a function which behaves like this. Is 1 over p plus I gamma. And gamma is some complex. Let us say that gamma is a positive real number. So it is a function that has a pole in the complex plane at point minus I gamma. So it's complex plane of momentum p.
So P can be complex.
Hmm?
P can be complex.
Of course, since we have this function defined on the real line, but we can immediately extend it to the whole complex plane. So, let us compute the Fourier transform of this function, or the inverse Fourier transform. Mhm. So, uh, this is f tilde. So f of x conjecturally equals to integral from minus infinity to plus infinity of d p over 2 pi e to the I p x over p plus I gamma. So to compute this integral, we will use complex analysis. So namely the method of residues. So if we have an integral of a complex function over some, so the main idea of this method is the following. If we have an integral of a complex analytic function along some contour, then we can deform this contour at least with singularity of a function. Uh, uh, so mm, Our original problem is to compute uh, maybe we formulate it as some statement. The lemma or theorem. So, but in any case, it is some simple statement that if you have two integrals over mm, two different contours of a function, let's call it f of p dv over some contour c1 and over some other contour c2, and this integrals are equal. If if our function f of p is analytic in the domain that is contained between these two contours in D, such that boundary of the domain is difference of these two contours. C1 minus C2, C2 minus C1, in this case C2 minus C1. So the idea, and this is true because if so some kind of proof of the statement, proof of the statement is that the integral over sufficiently small uh, over the boundary of sufficiently small domain of analytic function is zero.
Doesn't that follow from the residue theorem, what we're trying to prove?
I'm trying to prove the residue theorem in the simplest possible way. Hmm? Yeah. We want to prove that we can do arbitrary deformation of a contour, and to do this, I want first to perform a sufficiently small variation of a contour. Uh, uh, so we want to say why it is true. So this is true because we can expand f of p as a Taylor series around some point inside D. So P0. We can say that f of p is some from n equals to 0 to infinity p minus p0 to power n derivative of n at p0. So it's true for the analytic function. And if you compute this integral in this Taylor series, so probably where is this? So we have our domain D, have some point P0 in this domain, and we have a boundary of this domain. So there is a Taylor series around this point. So there are some estimations of its radius of convergence, but at the moment we don't care about them. Yeah. So we can take this Taylor series and simply integrate it term by term. So we can denote that g of p is in the integral, for example, from p0. P0 to p, f of p prime dp prime. And if you substitute this Taylor series, then we get simply that it is a sum from n equals to 0 to infinity, p minus p0 to n plus 1 over n plus 1 f n of p0. So, and now we see that this function is single valued on contour dd. So let us draw this contour as an open contour. So this point P0 we have this integral going from P initial to P final, when P initial actually equals to P final. So, integral over boundary of our function f of t, p equals to g of t final minus g of p initial, which equals to 0, since it's since this function is single valued. So So in this way, we can take any contour and perform a small modification of it. So there was a control C, and we can change it by such a domain D, by boundary of some domain. So we can draw the same contour slightly modified. So this is allowed. And so this is what we can do with controls. We can move them in whatever way until we meet singularities of function under the integral. And now the next question: what happens at this at the singularities? Around right, isolated. So in those cases, uh, uh, so I'll not prove this theorem, but there is a theorem that in those cases function f can be expanded as a Laurent series from depending on singularities. But let us actually restrict ourselves to cases when this function star is expanded as a finite Laurent series in a sense with finite number of negative terms. So let us say that now P0 is a singularity. And our function f of t has an expansion of this kind. From minus n to infinity, p minus p0 to n cn. It's called Laurent series. So let's try to compute its integral again. So integral, in this case, we write simply indefinite integral because there is a singularity. And we cannot start integrating from P0. So indefinite integral of f is the integral to point P, d prime, f of P prime. So, and in principle, we understand that the same formula as here can be written also in this case. From n equals to minus n to infinity, p minus p0 to n plus 1 over n plus 1 cn. We can write such an integral. But there is one problem here, that if n equals minus 1, this expression does not exist. So we should write n is different from -1. So, and who knows, what should we write for n equals -1? Hmm? Times no, why 2 pi? Yes, yes. Logarithm of p minus p0. Right. So now this function is not single valued. And in this case, the integral around the boundary of this domain D of f of p g e equals to g of p final minus g of p initial. And what does it equal to? Looking at this expression and at this picture. So argument of p minus p0 increases by 2 pi when we go around this circle. No, but you are using some formulas and yeah. But let us think about this. So you have a p minus p0. We know that a complex number that describes p can be written as p0. So.
It's because the argument of Pf is 2 pi I more the argument of
Well, argument is.
Pf minus p0 is 2 pi I more
Mm,
of the argument of
uh,
I minus p0.
Yes, I would say so. People call argument this expression without I, so I would say that they differ by 2 pi. But yes, so in this exponential representation, log of p minus p0 is log of r, which does not change, plus I phi, and this phi goes from 0 to 2 pi. So phi initial is, for example, 0. Or maybe better to write that phi final is phi initial plus 2 pi. So this difference equals to 2 pi I times c minus 1. And this equals, by definition, to pi I times residue of f at point p0. So this is c minus 1. Maybe I can write it here. So this, by definition, is a residue at point p0 0 f of p actually times dp. Because residues are well defined for functions at times differential. So there is a residue of one form, but not of a function, because if you change coordinate, for example, if you scale p by the factor of 2, then coefficient of f is not invariant, but coefficient of f times dp is invariant. So it is 2 pi I times residue of at p equals to p0 f of p dp. So it was for one domain, and mm, yeah, can I use this? So, and if you have an integral over some large domain that has many singularities, it can be reduced to sum of residues inside this domain. So, if you have some domain D with boundary dd, and we compute integral over the boundary of this domain, and there are some singularities pi. Mm. Integral over the boundary of this domain, function of pdp is equal to 2 pi I times sum of residues. It points pi of so isn't the proof of the statement more or less obvious? Uh, so, uh, proof can be given simply by drawing pictures. In a sense, we take this original domain and transform it and shrink it to this collection of poles by small movements. So we can deform it to something like this, close to all the singularities, and even further, it can be reduced to a contour and certain only the set of singularities. And each individual integral can be computed using this approach. We simply integrate it locally and look at the jump. So uh, it, it, it's kind of simple. Mm. Uh, but here we have a little bit different situation. where is our integral? So it's there. In our situation, this integral is not over the finite domain, but over the real line. So that's our integral. So we have the integral from minus infinity to plus infinity of e to the I, maybe minus, no, I px, or pi p plus I gamma. And let us choose some value of x. Let us say that x is positive. Let x be greater than 0. So in this case, mm, the function in the numerator decays when p, when imaginary part of p is large. So it can be written as e to the I real part of p x times, well, it can be written in this way in any case, but in our situation, in this particular situation, we can say that this term x times the imaginary part of p goes to 0, and goes to 0 very fast. If imaginary part of p goes to plus infinity, it goes to 0. If goes to plus infinity. So using this property, we can do the following. We can say that this integral, the contour of integration can be completed to the closed contour that goes in the upper half plane. So so this integral from minus infinity to plus infinity, I px p over p plus I gamma can be computed as a limit from for r going to infinity of the integral over the contour c c plus r of the same function. And this c plus r looks like this. Because the integral over the upper arc. So this is C plus R. Because it's easy to see that the integral over the upper arc goes to 0 when r goes to infinity. Because if you go sufficiently high in the imaginary part uh, p, then everything is dominated by the exponential. And if you compute the integral over this small part close to the real line, it will go to 0 because it contains p in the denominator. So it goes to 0 at least as 1 over r. So, so this function simply goes to 0 in all this in all points of this large contour. Right? Uh, So since we have this, well, and now we can say immediately what the value of this integral is. Yes, yes. So, so we have a function that vanishes for the that vanishes on the whole. In this case, positive line. Uh, so let us compute it for a negative value of x. Maybe let me keep this formula here and let me erase this.
So this function is just x equals 0 in real space?
Hmm?
The function is just x equals 0 in real space?
Oh, who is x?
Well, we're integrating out p, so we have a function of x.
Yes, so it equals to 0 for positive x. So, and it's so you may see here that if a function goes to 0 when p goes to infinity, and if it is analytic in the upper half plane, then it vanishes for then its Fourier image vanishes for positive axis. So it's a general phenomenon. So now let's consider the opposite case. Let x be less than 0. Then we can apply the same logic, but now this contour will be closed in the lower half plane. So integral from minus infinity to plus infinity e to I px dp or p plus I gamma equals to a limit from r to infinity integral over c r, right, on the same function. And this contour is closed in the lower half plane. because now this expression goes to zero when a imaginary part of P goes to minus infinity. The P-plane. And in this case, situation is different because we have a point minus a gamma. So who knows how to compute this integral?
Use our
Hmm?
Use our resident theorem.
Of course, in a sense, we have a contour and we have a single residue inside this contour.
We substitute to P minus I gamma to get
Hmm?
to the gamma x
E to the
gamma x.
well, it is I times minus I gamma times x, right? Uh, Multiplied by uh, mm, minus 1 because the orientation is clockwise.
Yes. And then times 2 pi pi.
Yes, and divide by 2 pi, which was originally in this integral. So this is this comes from the clockwise orientation. Mm. So in total, it is uh, minus I e to gamma x. So the answer for this function is the following. It is 0 for a positive x, and it is minus I e to gamma x for x negative. So we can write it equivalently that it is a heaviside theta of x minus I heaviside theta of x times e to of minus x times e to gamma x. So neglecting this minus I factor, we can draw this function like this. The function that is discontinuous well, already the function itself is discontinuous at 0. So it's decaying at minus infinity and is 0 for positive x. We can absolute value of, or maybe absolute value of f of x. Right.
I missed the step over here because our Fourier coefficient is complex exponential, but then when we restrict x greater to 0, we need the exponent to be negative and real to decay. So when does it become a real exponent?
Oh, wait, could you say it again?
in the last one,
so we had
you broke it up into real and complex, and then the real part does decay, so the complex part also goes away.
yes. In sense, complex part is just a phrase, and we don't care about that. Yeah. So yeah, but so what I wanted to show here is this phenomenon that which was predicted precisely by this computation. So we had some function that was discontinuous at zero, uh, in a sense that well, probably we should substitute here something like c minus 1, or maybe better to redo this integration by parts, assuming that already the function itself is not continuous. So we can only integrate it by parts once and get 1 over n in the asymptotics. And we see this behavior. So in a sense, we can say that this C is a kind of in C C minus 1 in the sense that integral of this function will be continuous. And we recover this 1 over n behavior, or in this case, 1 over x behavior for 1 over p behavior for HP. So uh, and also to make sure that we have computed this transformation correctly, let us quickly compute the inverse transformation. Okay. So we want to compute the integral from minus infinity to plus infinity of minus I theta heaviside of minus x e to gamma x e to minus I p x. So we can restrict this dx. We can restrict this integral to the half line and invert the domain of integration. So it will be the integral from minus I, integral from 0 to plus infinity, theta, well, e to minus gamma x, e to I px dx. So it equals to minus I. Well, I can already compute it. Just minus I, 1 over. By the way, can you compute it immediately?
Negative gamma plus IP.
No, I would say like this. If you hide the second exponential, this integral will equal to 1 over gamma. It is some positive number, so what else can it be? 1 over gamma. And when you add the exponential, then you add a complex correction to gamma with a negative sign. So it will be gamma minus I p. And so altogether it is 1 over p plus I gamma. Uh, so, uh, we see this asymptotic property. We see that the functions, two functions are actually inverse, and we can also make the following remark that as we proved, the sum of absolute values squared of Fourier coefficients should be convergent, and this fact has a natural generalization to the real line that. And that integral of absolute value squared of this function is also convergent. dp over absolute value, oh, absolute value of 1 over p plus I gamma squared dp over 2 pi is less than infinity. So it is also convergent. So since we started from more or less well-behaved function. Okay, so thanks for your attention. Well, next time we will finish this program about the Fourier transform, and we'll apply it in some cases. So, hold on.